In mathematics, the Riemann hypothesis, proposed by Bernhard Riemann, 1859, is a conjecture that the non-trivial zeros of the Riemann zeta function all have real part 1/2. The name is also used for some closely related analogues, such as the Riemann hypothesis for curves over finite fields. The Riemann hypothesis implies results about the distribution of prime numbers. Along with suitable generalizations, some mathematicians consider it the most important unresolved problem in pure mathematics. The Riemann hypothesis, along with the Goldbach conjecture, is part of Hilbert's 8th problem in David Hilbert's list of 23 unsolved problems. It is also one of the Clay Mathematics Institute Millennium Prize problems. The Riemann zeta function I(s) is a function whose argument s may be any complex number other than 1, and whose values are also complex. It has zeros at the negative even integers. That is, I(s), a equals a0 when s is 1 of a 2, a 4, a 6, these are called its trivial zeros. However, the negative even integers are not the only values for which the zeta function is 0. The other ones are called non-trivial zeros. The Riemann hypothesis is concerned with the locations of these non-trivial zeros, and states that the real part of every non-trivial zero of the Riemann zeta function is 1/2. Thus, if the hypothesis is correct, all the non-trivial zeros lie on the critical line consisting of the complex numbers 1/2 plus e⁻ℏt, where t is a real number and I is the imaginary unit. There are several non-technical books on the Riemann hypothesis, such as Derbyshire, Rockamore du Sautoy. The books Edwards, Patterson, Bowenale and Mazur and Stein give mathematical introductions, while Titchmarsh, Ivia and Karatsever and Voronin are advanced monographs. Riemann zeta function. The Riemann zeta function is defined for complex S with real part greater than 1 by the absolutely convergent infinite series. Leonhard Euler showed that this series equals the Euler product, where the infinite product extends over all prime numbers p, and again converges for complex S with real part greater than 1. The convergence of the Euler product shows that I(s) has no zeros in this region, as none of the factors have zeros. The Riemann hypothesis discusses zeros outside the region of convergence of this series, so it must be analytically continued to all complex S. This can be done by expressing it in terms of the Dirichlet eta function as follows. If the real part of S is greater than 1, then the zeta function satisfies. However, the series on the right converges not just when S is greater than 1, but more generally whenever S has positive real part. Thus, this alternative series extends the zeta function from s 1 to the larger domain s 0, excluding the zeros of. The zeta function can be extended to these values, as well, by taking limits, giving a finite value for all values of S with positive real part except for a simple pole at r equals a1. In the strip 0, s 1 the zeta function satisfies the functional equation. One may then define I(s) for all remaining non-zero complex numbers S by assuming that this equation holds outside the strip as well, and letting I(s) equal the right-hand side of the equation whenever S is non-positive real part. If S is a negative even integer then I(s) equals 0 because the factor sin, I(s)/2, vanishes. These are the trivial zeros of the zeta function. The value I(0) equals a1/2 is not determined by the functional equation, but is the limiting value of I(s), as S approaches 0. The functional equation also implies that the zeta function has no zeros with negative real part other than the trivial zeros, so all non-trivial zeros lie in the critical strip where S is real part between 0 and 1. History. In his 1859 paper on the number of primes less than a given magnitude, Riemann found an explicit formula for the number of primes x less than a given number x. His formula was given in terms of the related function, which counts the primes and prime powers up to x, counting a prime power Pn as 1/n of a prime. The number of primes can be recovered from this function by where I1/4 is the Mach paragraph bias function. Riemann's formula is then where the sum is over the non-trivial zeros of the zeta function and where I0 is a slightly modified version of I that replaces its value at its points of discontinuity by the average of its upper and lower limits. The summation in Riemann's formula is not absolutely convergent, but may be evaluated by taking the zeros I in order of the absolute value of their imaginary part. The function Lie occurring in the first term is the logarithmic integral function given by the Cauchy principal value of the divergent integral. The terms Lie, Xi, involving the zeros of the zeta function need some care in their definition as Lie has branch points at 0 and 1, and are defined by analytic continuation in the complex variable I in the region Re, I, AA0, that is they should be considered as AE, ILNX. The other terms also correspond to zeros. The dominant term Lie, X, comes from the pole at Xi equals A1, considered as a zero of multiplicity A1, and the remaining small terms come from the trivial zeros. For some graphs of the sums of the first few terms of this series see Rizal and Gar paragraph HL or Zagier. This formula says that the zeros of the Riemann zeta function control the oscillations of primes around their expected positions. Riemann knew that the non-trivial zeros of the zeta function were symmetrically distributed about the line S equals 1/2 plus it, and he knew that all of its non-trivial zeros must lie in the range 0 a per mille currency Re, S, a per mille 1 currency. He checked that a few of the zeros lay on the critical line with real part 1/2 and suggested that they all do. This is the Riemann hypothesis. Consequences of the Riemann hypothesis. The practical uses of the Riemann hypothesis include many propositions known true under the Riemann hypothesis, and some that can be shown equivalent to the Riemann hypothesis. Distribution of prime numbers. Riemann's explicit formula for the number of primes less than a given number in terms of a sum over the zeros of the Riemann zeta function says that the magnitude of the oscillations of primes around their expected position is controlled by the real parts of the zeros of the zeta function. In particular, the error term in the prime number theorem is closely related to the position of the zeros. For example, the supremum of real parts of the zeros is the infimum of numbers I squared such that the error is O, Xi squared, Ingham 1932. Von Koch proved that the Riemann hypothesis is equivalent to the best possible bound for the error of the prime number theorem. A precise version of Koch's result, due to Schoenfeld, says that the Riemann hypothesis is equivalent to. Schoenfeld also showed that the Riemann hypothesis is equivalent to where I, X, is Chebyshev's second function. Growth of arithmetic functions. The Riemann hypothesis implies strong bounds on the growth of many other arithmetic functions, in addition to the primes counting function above. One example involves the Marr paragraph bias function I1/4. The statement that the equation is valid for every S with real part greater than 1/2, with the sum on the right-hand side converging, is equivalent to the Riemann hypothesis. From this we can also conclude that if the Mertens function is defined by, then the claim that for every positive I micron is equivalent to the Riemann hypothesis. The determinant of the order n Radeffer matrix is equal to m, n, so the Riemann hypothesis can also be stated as a condition on the growth of these determinants. The Riemann hypothesis puts a rather tight bound on the growth of M, since Odlyzko and T. E. Real disproved the slightly stronger Mertens conjecture. The Riemann hypothesis is equivalent to many other conjectures about the rate of growth of other arithmetic functions aside from I1/4, n. A typical example is Robin's theorem, which states that if I florin, n, is the divisor function, given by, then for all n greater than 50/40 if and only if the Riemann hypothesis is true, where I cubed is the Euler-Mascaroni constant. Another example was found by Jar copyright Rami Fresnel, and extended by Landau. The Riemann hypothesis is equivalent to several statements showing that the terms of the Fairy sequence are fairly regular. One such equivalence is as follows: if Fn is the Fairy sequence of order n, beginning with 1/n and up to 1/1, then the claim that for all I micron 0 is equivalent to the Riemann hypothesis. Here is the number of terms in the Fairy sequence of order n. For an example from group theory, if G, n, is Landau's function given by the maximal order of elements of the symmetric group Sn of degree n. Then Massias, Nicholas and Robin showed that the Riemann hypothesis is equivalent to the bound for all sufficiently large n. Lindelöf paragraph F hypothesis and growth of the zeta function. The Riemann hypothesis has various weaker consequences as well. One is the Lindelöf paragraph F hypothesis on the rate of growth of the zeta function on the critical line, which says that, for any I micron 0 as a TAA. The Riemann hypothesis also implies quite sharp bounds for the growth rate of the zeta function in other regions of the critical strip. For example, it implies that so the growth rate of I paragraph, 1 plus it, and its inverse would be known up to a factor of 2. Large prime gap conjecture. The prime number theorem implies that on average, the gap between the prime p and its successor is log p. However, some gaps between primes may be much larger than the average. Kramer copywriter proved that, assuming the Riemann hypothesis, every gap is O, ASHPA log p. This is a case in which even the best bound that can be proved using the Riemann hypothesis is far weaker than what seems true. Kramer copywriter's conjecture implies that every gap is O log p, 2, which, while larger than the average gap, is far smaller than the bound implied by the Riemann hypothesis. Numerical evidence supports Kramer copywriter's conjecture. Criteria equivalent to the Riemann hypothesis. Many statements equivalent to the Riemann hypothesis have been found, though so far none of them have led to much progress in proving it. Some typical examples are as follows. The Rice criterion was given by Rice, to the effect that the bound holds for all I micron 0 if and only if the Riemann hypothesis holds. Neumann proved that the Riemann hypothesis is true if and only if the space of functions of the form where I, z, is the fractional part of z, 0 a permale currency I 1/2 a permale 1 currency, and is dense in the Hilbert space L2, 0, 1, of square integrable functions on the unit interval. Beerling extended this by showing that the zeta function has no zeros with real part greater than 1/p if and only if this function space is dense in LP, 0, 1. Salem showed that the Riemann hypothesis is true if and only if the integral equation has no non-trivial bounded solutions for. Weil's criterion is the statement that the positivity of a certain function is equivalent to the Riemann hypothesis. Related is Lee's criterion, a statement that the positivity of a certain sequence of numbers is equivalent to the Riemann hypothesis. Spiesa proved that the Riemann hypothesis is equivalent to the statement that the derivative of I paragraph, S, has no zeros in the strip. That I paragraph has only simple zeros on the critical line is equivalent to its derivative having no zeros on the critical line. Consequences of the generalized Riemann hypothesis. Several applications use the generalized Riemann hypothesis for Dirichlet L-series or zeta functions of number fields rather than just the Riemann hypothesis. Many basic properties of the Riemann zeta function can easily be generalized to all Dirichlet L-series, so it is plausible that a method that proves the Riemann hypothesis for the Riemann zeta function would also work for the generalized Riemann hypothesis for Dirichlet L functions. Several results first proved using the generalized Riemann hypothesis were later given unconditional proofs without using it, though these were usually much harder. Many of the consequences on the following list are taken from Conrad. In 1913, Groenewald showed that the generalized Riemann hypothesis implies that Gauss's list of imaginary quadratic fields with class number 1 is complete, though Baker, Stark and Hefner later gave unconditional proofs of this without using the generalized Riemann hypothesis. In 1917, Hardy and Littlewood showed that the generalized Riemann hypothesis implies a conjecture of Chebyshev that which says that in some sense primes 3 mod 4 are more common than primes 1 mod 4. In 1923 Hardy and Littlewood showed that the generalized Riemann hypothesis implies a weak form of the Goldbach conjecture for odd numbers, that every sufficiently large odd number is the sum of 3 primes, though in 1937 Vinogradov gave an unconditional proof. In 1997 Deschnellers, Effinger, T. E. Real, and Zinoviev showed that the generalized Riemann hypothesis implies that every odd number greater than 5 is the sum of 3 primes. In 1934, Schauler showed that the generalized Riemann hypothesis implies that the first prime in the arithmetic progression mod m is at most km2 log m2 for some fixed constant k. In 1967, Hooley showed that the generalized Riemann hypothesis implies Artin's conjecture on primitive roots. In 1973, Weinberger showed that the generalized Riemann hypothesis implies that Euler's list of ideal numbers is complete. Weinberger showed that the generalized Riemann hypothesis for the zeta functions of all algebraic number fields implies that any number field with class number 1 is either Euclidean or an imaginary quadratic number field of discriminant a 19, a 43, a 67, or a 163. In 1976, G. Miller showed that the generalized Riemann hypothesis implies that one can test if a number is priming polynomial time via the Miller test. In 2002, Munindra Agrawal, Neeraj Kaul and Nitin Saxena proved this result unconditionally using the AKS primality test. Odlytsko discussed how the generalized Riemann hypothesis can be used to give sharper estimates for discriminants and class numbers of number fields. Ono and Soundararajan showed that the generalized Riemann hypothesis implies that Ramanujan's integral quadratic form x2 plus y2 plus 10z2 represents all integers that it represents locally, with exactly 18 exceptions. Excluded middle, some consequences of the RH are also consequences of its negation, and are thus theorems. In their discussion of the Heck-Turing Mordell, Heilbronn theorem, say, the method of proof here is truly amazing. If the generalized Riemann hypothesis is true, then the theorem is true. If the generalized Riemann hypothesis is false, then the theorem is true. Thus, the theorem is true. Care should be taken to understand what is meant by saying the generalized Riemann hypothesis is false. One should specify exactly which class of Dirichlet series has a counterexample. Littlewood's theorem. This concerns the sign of the error in the prime number theorem. It has been computed that a euro, x, li, x, for all xa per mil 1023 currency, and no value of x is known for which a euro, x, li, x. See this table. In 1914 Littlewood proved that there are arbitrarily large values of x for which, and that there are also arbitrarily large values of x for which. Thus the difference a euro, x, a li, x, changes sign infinitely many times. Skew's number is an estimate of the value of x corresponding to the first sign change. Littlewood's proof is divided into two cases, the RH is assumed false, and the RH is assumed true. Gauss's class number conjecture. This is the conjecture that there are only a finite number of imaginary quadratic fields with a given class number. One way to prove it would be to show that as the discriminant DAAA the class number H, D, AA. The following sequence of theorems involving the Riemann hypothesis is described in Ireland and Rosen 1990, ppA 358 to Euro 361. Theorem. Let D less than 0 be the discriminant of an imaginary quadratic number field K. Assume the generalized Riemann hypothesis for L functions of all imaginary quadratic Dirichlet characters. Then there is an absolute constant C such that. Theorem. If the RH is false then H, D, 1 if D is sufficiently large. Theorem. If the RH is false then H, D, AA is DAAA. Theorem. If the generalized RH is false for the L function of some imaginary quadratic Dirichlet character then H, D, AA is DAAA. In the work of Heck and Heilbronn, the only L functions that occur are those attached to imaginary quadratic characters, and it is only for those L functions that GRH is true or GRH is false is intended. A failure of GRH for the L function of a cubic Dirichlet character would, strictly speaking, mean GRH is false, but that was not the kind of failure of GRH that Heilbronn had in mind, so his assumption was more restricted than simply GRH is false. In 1935, Carl Siegel later strengthened the result without using RH or GRH in any way. Growth of Euler's totient. In 1983 J. L. Nicholas proved that for infinitely many n, where I, n, is Euler's totient function and I cubed is Euler's constant, Riebenboim remarks that the method of proof is interesting, in that the inequality is shown first under the assumption that the Riemann hypothesis is true, secondly under the contrary assumption. Generalizations and analogues of the Riemann hypothesis, Dirichlet L-series and other number fields. The Riemann hypothesis can be generalized by replacing the Riemann zeta function by the formally similar, but much more general, global L functions. In this broader setting, one expects the non-trivial zeros of the global L functions to have real part 1/2. It is these conjectures, rather than the classical Riemann hypothesis only for the single Riemann zeta function, which account for the true importance of the Riemann hypothesis in mathematics. The generalized Riemann hypothesis extends the Riemann hypothesis to all Dirichlet L functions. In particular, it implies the conjecture that Siegel zeros do not exist. The extended Riemann hypothesis extends the Riemann hypothesis to all Dedekind zeta functions of algebraic number fields. The extended Riemann hypothesis for abelian extension of the rationals is equivalent to the generalized Riemann hypothesis. The Riemann hypothesis can also be extended to the L functions of Heck characters of number fields. The grand Riemann hypothesis extends it to all automorphic zeta functions, such as Mellin transforms of Heck eigenforms. Function fields and zeta functions of varieties over finite fields. Artin introduced global zeta functions of function fields and conjectured an analog of the Riemann hypothesis for them, which has been proven by Haas in the genus 1 case and by Weil in general. For instance, the fact that the Gauss sum, of the quadratic character of a finite field of size Q, has absolute value, is actually an instance of the Riemann hypothesis in the function field setting. This led Weil to conjecture a similar statement for all algebraic varieties. The resulting Weil conjectures were proven by Pierre de Lignier, 1974, 1980. Arithmetic zeta functions of arithmetic schemes and their L factors. Arithmetic zeta functions generalize the Riemann and Dedekind zeta functions as well as the zeta functions of varieties over finite fields to every arithmetic scheme or a scheme of finite type over integers. The arithmetic zeta function of a regular connected equidimensional arithmetic scheme of Kronecker dimension n can be factorized into the product of appropriately defined L factors and an auxiliary factor. Jean-Pierre Serre, 1970. Assuming a functional equation and meromorphic continuation, the generalized Riemann hypothesis for the L factor states that its zeros inside the critical strip lie on the central line. Correspondingly, the generalized Riemann hypothesis for the arithmetic zeta function of a regular connected equidimensional arithmetic scheme states that its zeros inside the critical strip lie on vertical lines and its poles inside the critical strip lie on vertical lines. This is known for schemes in positive characteristic and follows from Pierre de Lignier, 1974, 1980, but remains entirely unknown in characteristic zero. Selberg zeta functions. Selberg introduced the Selberg zeta function of a Riemann surface. These are similar to the Riemann zeta function, they have a functional equation, and an infinite product similar to the Euler product but taken over closed geodesics rather than primes. The Selberg trace formula is the analog for these functions of the explicit formulas in prime number theory. Selberg proved that the Selberg zeta functions satisfy the analog of the Riemann hypothesis, with the imaginary parts of their zeros related to the eigenvalues of the Laplacian operator of the Riemann surface. Iara zeta functions. The Iara zeta function of a finite graph is an analog of the Selberg zeta function introduced by Yasutaka Iara. A regular finite graph is a Ramanujan graph, a mathematical model of efficient communication networks, if and only if its Iara zeta function satisfies the analog of the Riemann hypothesis as was pointed out by T. Sunada. Montgomery's pair correlation conjecture. Montgomery suggested the pair correlation conjecture that the correlation functions of the zeros of the zeta function should be the same as those of the eigenvalues of a random Hermitian matrix. Odlyzko showed that this is supported by large-scale numerical calculations of these correlation functions. Montgomery showed that at least two-thirds of all zeros are simple, and a related conjecture is that all zeros of the zeta function are simple. Dedekind zeta functions of algebraic number fields, which generalize the Riemann zeta function, often do have multiple complex zeros. This is because the Dedekind zeta functions factorize as a product of powers of Rt in L functions, so zeros of Rt in L functions sometimes give rise to multiple zeros of Dedekind zeta functions. Other examples of zeta functions with multiple zeros are the L functions of some elliptic curves. These can have multiple zeros at the real point of their critical line. The Birch-Swinnerton and Dyer conjecture predicts that the multiplicity of this zero is the rank of the elliptic curve. Other zeta functions. There are many other examples of zeta functions with analogues of the Riemann hypothesis, some of which have been proved. Gauss zeta functions of function fields have a Riemann hypothesis, proved by Schaets. The main conjecture of I-Weisser theory, proved by Barry Mazur and Andrew Wiles for cycloatomic fields, and Wiles for totally real fields, identifies the zeros of a p-adic L function with the eigenvalues of an operator, so can be thought of as an analogue of the Hilbert-Pascal-Kuebler conjecture for p-adic L functions. Attempts to prove the Riemann hypothesis. Several mathematicians have addressed the Riemann hypothesis, but none of their attempts have yet been accepted as correct solutions. Watkins lists some incorrect solutions, and more are frequently announced. Operator theory. Hilbert and Polya suggested that one way to derive the Riemann hypothesis would be to find a self-adjoint operator, from the existence of which the statement on the real parts of the zeros of I paragraph, S, would follow when one applies the criterion on real eigenvalues. Some support for this idea comes from several analogues of the Riemann zeta functions whose zeros correspond to eigenvalues of some operator. The zeros of a zeta function of a variety over a finite field correspond to eigenvalues of a Frobenius element on an A-copyright tail cohomology group. The zeros of a Selberg zeta function are eigenvalues of a Laplacian operator of a Riemann surface, and the zeros of a p-adic zeta function correspond to eigenvectors of a Gauss action on ideal class groups. Odlyzko showed that the distribution of the zeros of the Riemann zeta function shares some statistical properties with the eigenvalues of random matrices drawn from the Gaussian unitary ensemble. This gives some support to the Hilbert-Pascal-Kuebler conjecture. In 1999, Michael Berry and John Keating conjectured that there is some unknown quantization of the classical Hamiltonian H equals xp so that, and even more strongly, that the Riemann zeros coincide with the spectrum of the operator. This is in contrast to canonical quantization, which leads to the Heisenberg uncertainty principle and the natural numbers as spectrum of the quantum harmonic oscillator. The crucial point is that the Hamiltonian should be a self-adjoint operator so that the quantization would be a realization of the Hilbert-Pascal-Kuebler program. In a connection with this quantum mechanical problem, Berry and Combs had proposed that the inverse of the potential of the Hamiltonian is connected to the half derivative of the function. Then, in Berry-Combs approach. Combs 1999. This yields to a Hamiltonian whose eigenvalues are the square of the imaginary part of the Riemann zeros, and also the functional determinant of this Hamiltonian operator is just the Riemann xi function. In fact, the Riemann xi function would be proportional to the functional determinant. As proven by Combs and others, in this approach, the analogy with the Riemann hypothesis over finite fields suggests that the Hilbert space containing eigenvectors corresponding to the zeros might be some sort of first cohomology group of the spectrum spec, Z, of the integers. Dieninga described some of the attempts to find such a cohomology theory. Zagier constructed a natural space of invariant functions on the upper half-plane that has eigenvalues under the Laplacian operator that correspond to zeros of the Riemann zeta function euro, and remarked that in the unlikely event that one could show the existence of a suitable positive definite inner product on this space, the Riemann hypothesis would follow. Katia discussed a related example, where due to a bizarre bug a computer program listed zeros of the Riemann zeta function as eigenvalues of the same Laplacian operator. Shamir and Hutchinson surveyed some of the attempts to construct a suitable physical model related to the Riemann zeta function. Loewy-Yang theorem. The Loewy-Yang theorem states that the zeros of certain partition functions in statistical mechanics all lie on a critical line with real part zero, and this has led to some speculation about a relationship with the Riemann hypothesis. Tura-N's result, par el Tura-Na, 1948, showed that if the functions have no zeros when the real part of S is greater than 1, then where I, n, is the Liouville function given by if n has r prime factors. He showed that this in turn would imply that the Riemann hypothesis is true. However, Haselgrove proved that T, x, is negative for infinitely many x, and Bowain, Ferguson and Mossingoff showed that the smallest such x is 72,185,376,951,205. Spira showed by numerical calculation that the finite Dirichlet series above for n equals 19 has a zero with real part greater than 1. Tura n also showed that a somewhat weaker assumption, the non-existence of zeros with real part greater than 1 plus n 1/2 plus I micron for large n in the finite Dirichlet series above, would also imply the Riemann hypothesis, but Montgomery showed that for all sufficiently large n these series have zeros with real part greater than 1 plus / for log n. Therefore, Tura n's result is vacuously true and cannot be used to help prove the Riemann hypothesis. Non-commutative geometry, Kaniza, 1999, 2000, has described a relationship between the Riemann hypothesis and non-commutative geometry, and shows that a suitable analogue of the Selberg trace formula for the action of the ideal class group on the ideal class space would imply the Riemann hypothesis. Some of these ideas are elaborated in Lapidus. Hilbert spaces of entire functions, Louis de Brangezer, 1992. Showed that the Riemann hypothesis would follow from a positivity condition on a certain Hilbert space of entire functions. However, Conray and Lee showed that the necessary positivity conditions are not satisfied. Quasicrystals, the Riemann hypothesis implies that the zeros of the zeta function form a quasicrystal, meaning a distribution with discrete support whose Fourier transform also has discrete support. Dyson suggested trying to prove the Riemann hypothesis by classifying, or at least studying, one-dimensional quasicrystals. Arithmetic zeta functions of models of elliptic curves over number fields, when one goes from geometric dimension 1, for example an algebraic number field, to geometric dimension 2, for example a regular model of an elliptic curve over a number field, the two-dimensional part of the generalized Riemann hypothesis for the arithmetic zeta function of the model deals with the poles of the zeta function. In dimension 1 the study of the zeta integral in Tate's thesis does not lead to new important information on the Riemann hypothesis. Contrary to this, in dimension 2 work of Ivan Fisenko on two-dimensional generalization of Tate's thesis includes an integral representation of a zeta integral closely related to the zeta function. In this new situation, not possible in dimension 1, the poles of the zeta function can be studied via the zeta integral and associated Adel groups. Related conjecture of Fisenko, 2010, on the positivity of the fourth derivative of a boundary function associated to the zeta integral essentially implies the pole part of the generalized Riemann hypothesis. Suzukiya, 2011, proved that the latter, together with some technical assumptions, implies Fisenko's conjecture. Multiple zeta functions, Deline's proof of the Riemann hypothesis over finite fields used the zeta functions of product varieties, whose zeros and poles correspond to sums of zeros and poles of the original zeta function, in order to bound the real parts of the zeros of the original zeta function. By analogy, Kurokawa introduced multiple zeta functions whose zeros and poles correspond to sums of zeros and poles of the Riemann zeta function. To make the series converge he restricted to sums of zeros or poles all with non-negative imaginary part. So far, the known bounds on the zeros and poles of the multiple zeta functions are not strong enough to give useful estimates for the zeros of the Riemann zeta function. Location of the zeros, number of zeros, the functional equation combined with the argument principle implies that the number of zeros of the zeta function with imaginary part between 0 and t is given by for s equals 1/2 plus it, where the argument is defined by varying it continuously along the line with m, s, equals t, starting with argument 0 at a plus it. This is the sum of a large but well-understood term and a small but rather mysterious term. So the density of zeros with imaginary part near t is about log t/2 I euro, and the function s describes the small deviations from this. The function s, t, jumps by 1 at each zero of the zeta function, and for ta permulation it decreases monotonically between zeros with derivative close to a log t. Karatsuba proved that every interval, t plus h, for contains at least points where the function s, t, changes sign. Selberg showed that the average moments of even powers of s are given by. This suggests that s, t, log t, 1/2 resembles a Gaussian random variable with mean 0 and variance 2i2 proved this fact. In particular s, t, is usually somewhere around 1/2, but occasionally much larger. The exact order of growth of s, t, is not known. There has been no unconditional improvement to Riemann's original bound s, t, equals O, log t, though the Riemann hypothesis implies the slightly smaller bound s, t, equals O, log t log t. The true order of magnitude may be somewhat less than this, as random functions with the same distribution as s, t, tend to have growth of order about log t, 1/2. In the other direction it cannot be too small. Selberg showed that s, t, a permul log t, 1, log t, 7/3, and assuming the Riemann hypothesis Montgomery showed that s, t, a permul log t, 1, log t, 1/2. Numerical calculations confirm that s grows very slowly, s, t, aa1 for t less than 280, s, t, aa2 for t 6,800,000, and the largest value of s, t, found so far is not much larger than 3. Riemann's estimate s, t, a equals O, log t, implies that the gaps between zeros are bounded, and Littlewood improved this slightly, showing that the gaps between their imaginary parts tends to 0. Theorem of Hadamard and de la Valla copyright E. Poussin. Hadamard and de la Valla copyright E. Poussin independently proved that no zeros could lie on the line Re, s, equals 1. Together with a functional equation and the fact that there are no zeros with real part greater than 1, this showed that all non-trivial zeros must lie in the interior of the critical strip 0, Re, s, 1. This was a key step in their first proofs of the prime number theorem. Both the original proofs that the zeta function has no zeros with real part 1 are similar, and depend on showing that if I paragraph 1 plus it vanishes, then I paragraph 1 plus 2 it is singular, which is not possible. One way of doing this is by using the inequality. For I florin 1, t real, and looking at the limit as I florin a 1. This inequality follows by taking the real part of the log of the Euler product to see that where the sum is over all prime powers Pn, so that which is at least 1 because all the terms in the sum are positive, due to the inequality. Zero free regions. De la Valla copyright E. Poussin proved that if I florin plus E a euro sht is a zero of the Riemann zeta function, then 1 a I florin a per million c log t, for some positive constant c. In other words, zeros cannot be too close to the line I florin equals 1, there is a zero free region close to this line. This zero free region has been enlarged by several authors using methods such as Vinogradov's mean value theorem. Ford gave a version with explicit numerical constants, I paragraph, I florin plus E a euro st euro a per mil 0 whenever ta euro a per mil 3n and zeros on the critical line. Hardy and Littlewood showed there are infinitely many zeros on the critical line, by considering moments of certain functions related to the zeta function. Selberg proved that at least a positive proportion of zeros lie on the line. Levinson improved this to 1/3 of the zeros by relating the zeros of the zeta function to those of his derivative, and Conray improved this further to 2/5. Most zeros lie close to the critical line. More precisely, Bohr and Landau showed that for any positive I micron, all but an infinitely small proportion of zeros lie within a distance I micron of the critical line. Ivier gives several more precise versions of this result, called zero-density estimates, which bound the number of zeros in regions with imaginary part at most t and real part at least 1/2 plus I micron. Hardy Littlewood conjectures. In 1914 Godfrey Harold Hardy proved that has infinitely many real zeros. Let n, t, be the total number of real zeros, be the total number of zeros of odd order of the function lying on the interval 0, t. The next two conjectures of Hardy and John Edens are Littlewood on the distance between real zeros of and on the density of zeros of on intervals t plus h, for sufficiently large t greater than 0, and with as less as possible value of a greater than 0, where I micron 0 is an arbitrarily small number, open to new directions in the investigation of the Riemann zeta function. 1 for any I micron 0 there exists such that for and the interval contains a 0 of odd order of the function. 2 for any I micron 0 there exist and C equals C, I micron 0, such that for and the inequality is true. Selberg conjecture. This paragraph is not on Selberg's 1/4 conjecture but on Selberg's zeta function conjecture. Selberger, 1942, investigated the problem of Hardy-Littlewood 2 and proved that for any I micron 0 there exists such and C equals C, I micron 0, such that for and the inequality is true. Selberg conjectured that this could be tightened to Karatsubaya, 1984, 1984b, 1985, proved that for a fixed I micron satisfying the condition 0, I micron 0.001, a sufficiently large t and, the interval contains at least CHLN, t, real zeros of the Riemann zeta function and therefore confirmed the Selberg conjecture. The estimates of Selberg and Karatsubaya cannot be improved in respect of the order of growth as a TAA. Karatsubaya proved that an analogue of the Selberg conjecture holds for almost all intervals, t plus h, where I micron is an arbitrarily small fixed positive number. The Karatsubaya method permits to investigate zeros of the Riemann zeta function on super-short intervals of the critical line, that is, on the intervals t plus h, the length h of which grows slower than any, even arbitrarily small degree t. In particular, he proved that for any given numbers a micron, satisfying the conditions almost all intervals, t plus h, for contain at least zeros of the function. This estimate is quite close to the one that follows from the Riemann hypothesis. Numerical calculations. The function has the same zeros as the zeta function in the critical strip, and is real on the critical line because of the functional equation, so one can prove the existence of zeros exactly on the real line between 2 points by checking numerically that the function has opposite signs at these points. Usually one writes, where Hardy's function z and the Riemann-Siegel theta function I are uniquely defined by this in the condition that they are smooth real functions with I, 0, equals 0. By finding many intervals where the function z changes sign one can show that there are many zeros on the critical line. To verify the Riemann hypothesis up to a given imaginary part t of the zeros, one also has to check that there are no further zeros off the line in this region. This can be done by calculating the total number of zeros in the region and checking that it is the same as the number of zeros found on the line. This allows one to verify the Riemann hypothesis computationally up to any desired value of t. Some calculations of zeros of the zeta function are listed below. So far all zeros that have been checked are on the critical line and are simple. For tables of the zeros, see Haselgrove and Miller or Odlytsko. Gram points. A gram point is a point on the critical line 1/2 a plus it where the zeta function is real and non-zero. Using the expression for the zeta function on the critical line, I paragraph, 1/2 a plus it, equals z, t, AAAE, t, where Hardy's function, z, is real for real t, and I is the Riemann-Siegel theta function, we see that zeta is real when sin, I, t equals 0. This implies that I, t, is an integer multiple of I euro, which allows for the location of gram points to be calculated fairly easily by inverting the formula for I. They are usually numbered as Gn for n equals 0, 1. Where Gn is the unique solution of I, t, equals ni euro. Gram observed that there was often exactly 1 0 of the zeta function between any two gram points. Hutchinson called this observation Gram's law. There are several other closely related statements that are also sometimes called Gram's law, for example, nz, Gn, is usually positive, or z, t, usually has opposite sign at consecutive gram points. The imaginary parts I cubed n of the first few zeros and the first few gram points gn are given in the following table. The first failure of Gram's law occurs at the 127th0 and the gram point g126, which are in the wrong order. A gram point t is called good if the zeta function is positive at 1/2 plus it. The indices of the bad gram points where z has the wrong sign are 126, 134, 195, 211. A gram block is an interval bounded by two good gram points such that all the gram points between them are bad. A refinement of Gram's law called Rosser's rule due to Rosser, Yohe and Schoenfeld says that gram blocks often have the expected number of zeros in them, even though some of the individual gram intervals in the block may not have exactly 1 zero in them. For example, the interval bounded by G125 and G127 is a gram block containing a unique bad gram point G126, and contains the expected number 2 of zeros although neither of its two gram intervals contains a unique zero. Rosser et al. Checked that there were no exceptions to Rosser's rule in the first 3 million zeros, although there are infinitely many exceptions to Rosser's rule over the entire zeta function. Gram's rule and Rosser's rule both say that in some sense zeros do not stray too far from their expected positions. The distance of a zero from its expected position is controlled by the function s defined above, which grows extremely slowly. Its average value is of the order of 1/2, which only reaches 2 for t around 1024. This means that both rules hold most of the time for small t but eventually break down often. Indeed, Trajan showed that both Gram's law and Rosser's rule fail in a positive proportion of cases. To be specific, it is expected that in about 73% 1 zero is enclosed by two successive gram points, but in 14% no zero and in 13% 2 zeros are in such a gram interval on the long run. Arguments for and against the Riemann hypothesis. Mathematical papers about the Riemann hypothesis tend to be cautiously non-committal about its truth. Of authors who express an opinion, most of them, such as Riemann or Bombieri, imply that they expect that it is true. The few authors who express serious doubt about it include Ivier, who lists some reasons for being skeptical, and Littlewood, who flatly states that he believes it is false, and that there is no evidence whatever for it and no imaginable reason that it would be true. The consensus of the survey articles is that the evidence for it is strong but not overwhelming, so that while it is probably true there is some reasonable doubt about it. Some of the arguments for the Riemann hypothesis are listed by Sarnak, Conray, and Ivier, and include the following reasons. Several analogues of the Riemann hypothesis have already been proved. The proof of the Riemann hypothesis for varieties over finite fields by Deligne is possibly the single strongest theoretical reason in favor of the Riemann hypothesis. This provides some evidence for the more general conjecture that all zeta functions associated with automorphic forms satisfy a Riemann hypothesis, which includes the classical Riemann hypothesis as a special case. Similarly, Selberg zeta functions satisfy the analogue of the Riemann hypothesis, and are in some ways similar to the Riemann zeta function, having a functional equation and an infinite product expansion analogous to the Euler product expansion. However, there are also some major differences. For example, they are not given by Dirichlet series. The Riemann hypothesis for the Gauss zeta function was proved by Schaets. In contrast to these positive examples, however, some Epstein zeta functions do not satisfy the Riemann hypothesis, even though they have an infinite number of zeros on the critical line. These functions are quite similar to the Riemann zeta function, and have a Dirichlet series expansion and a functional equation, but the ones known to fail the Riemann hypothesis do not have an Euler product and are not directly related to automorphic representations. At first, the numerical verification that many zeros lie on the line seems strong evidence for it. However, analytic number theory has had many conjectures supported by large amounts of numerical evidence that turn out to be false. See Skew's number for a notorious example, where the first exception to a plausible conjecture related to the Riemann hypothesis probably occurs around 10,316. A counterexample to the Riemann hypothesis with imaginary part this size would be far beyond anything that can currently be computed using a direct approach. The problem is that the behavior is often influenced by very slowly increasing functions such as log t, that tend to infinity, but do so slowly that this cannot be detected by computation. Such functions occur in the theory of the zeta function controlling the behavior of its zeros. For example, the function s, t, above has average size around 1/2. As s, t, jumps by at least 2 at any counterexample to the Riemann hypothesis, one might expect any counterexamples to the Riemann hypothesis to start appearing only when s, t, becomes large. It is never much more than 3 as far as it has been calculated, but is known to be unbounded, suggesting that calculations may not have yet reached a region of typical behavior of the zeta function. Denjoy's probabilistic argument for the Riemann hypothesis is based on the observation that if I1/4, x, is a random sequence of 1s and a 1s then, for every I micron 0, the partial sums, the values of which are positions in a simple random walk, satisfy the bound. With probability 1, the Riemann hypothesis is equivalent to this bound for the Marr paragraph bias function I1/4 and the Mertens function m derived in the same way from it. In other words, the Riemann hypothesis is in some sense equivalent to saying that I1/4, x, behaves like a random sequence of coin tosses. When I1/4, x, is non-zero, its sign gives the parity of the number of prime factors of x. So informally the Riemann hypothesis says that the parity of the number of prime factors of an integer behaves randomly. Such probabilistic arguments in number theory often give the right answer, but tend to be very hard to make rigorous, and occasionally give the wrong answer for some results, such as Mayer's theorem. The calculations in Odlyzko show that the zeros of the zeta function behave very much like the eigenvalues of a random Hermitian matrix, suggesting that they are the eigenvalues of some self-adjoint operator, which would imply the Riemann hypothesis. However, all attempts to find such an operator have failed. There are several theorems, such as the weak Goldbach conjecture for sufficiently large odd numbers, that were first proved using the generalized Riemann hypothesis, and later shown to be true unconditionally. This could be considered as weak evidence for the generalized Riemann hypothesis, as several of its predictions turned out to be true. Lamar's phenomenon where two zeros are sometimes very close is sometimes given as a reason to disbelieve in the Riemann hypothesis. However, one would expect this to happen occasionally just by chance even if the Riemann hypothesis were true, and Odlyzko's calculations suggest that nearby pairs of zeros occurred just as often as predicted by Montgomery's conjecture. Patterson suggests that the most compelling reason for the Riemann hypothesis for most mathematicians is the hope that primes are distributed as regularly as possible. See also: Generalized Riemann hypothesis, Grand Riemann hypothesis, Hilbert's eighth problem, Millennium Prize problems, Riemann hypothesis for curves over finite fields. References. External links: American Institute of Mathematics, Riemann hypothesis, Apostel, Tom, Where Are the Zeros of Zeta of S? A poem about the Riemann hypothesis, sung by John Derbyshire. Bowain, Peter, The Riemann hypothesis, Conrad, K., Consequences of the Riemann hypothesis, Conray, J. Bryan. Farmer, David W., Equivalences to the Riemann hypothesis, Gordon, Xavier. Spa, Pascal, Computation of Zeros of the Zeta Functioner. Odlyzko, Andrew, Homepagia including papers on the zeros of the zeta function and tables of the zeros of the zeta function. Odlyzko, Andrew, Zeros of the Riemann zeta function, Conjectures and Computations as Slides of a Talk, Peg, ed., 10 trillion zeta zeros, Math Games Websiteer. A discussion of Xavier Gordon's calculation of the first 10 trillion non-trivial zeros, Pugh, Glenn, JavaPlot for Plotting Z, T. Rubinstein, Michael, Algorithm for Generating the Zeros. Du Sotoy, Marcus, Prime Numbers Get Hitched, Seed Magazine, Stein, William A., What is Riemann's Hypothesis, De Vries, Andreas, The Graph of the Riemann Zeta Function I Paragraph, S. A Simple Animated JavaPlot. Watkins, Matthew R., proposed proofs of the Riemann hypothesis, zeta grid, a distributed computing project that attempted to disprove Riemann's hypothesis. Closed in November 2005.